Observations. 70–80% composition of life is, somebody mumbled it, water. Yes, we're looking at H2O. Why might H2O be an interesting molecule to evaluate for qualitative observations?
Everything uses it.
Everything uses it, shows up in a lot of places. At what phase? All of them, right? Or all of the common ones. So that's one of the interesting things behind water. We have solid, liquid, and gas. And yes, those are my attempts at coming up with those individual phases. Please don't argue with those pictures. They're as close as I could get. So let's take a look at the far left, upper left. What phase do you think I'm aiming for?
Solid.
Yes, solid. Pen works. Middle bottom.
It's also solid there too.
Yeah, I know.
Liquid.
But we already got solid out of the way, so let's go with liquid. And the upper right?
Gas.
Gas. And of course the upper right is going to be the most difficult one to actually come up with a picture for, because all we can really see is the liquid phase, okay, or the gas. So it's hard to nail that one down. So we're at least seeing those bubbles move through it. That's our gas phase. So when we're talking about those individual phases, it's the same piece of chemical matter. It's just changing how it interacts with the world, which then means we see a different phase associated with it. So our matter will break down into those phases. As our textbook then addresses, we want to then classify those based on some simple observations, like shape, volume, and compressibility. So where do you want to start? Solid, liquid, or gas? Whoops. That's what happens when you push the button at the wrong time. Solid. What can you tell me about the shape of a solid? Right. If I just set a shape or set a bit of solid down, it's going to stay in the same shape. Okay, it's maintained or fixed. Right. It's not going to change on its own. Since we started with shape, let's go ahead and move through to our liquid. What happens with our liquid?
Liquid adapts to the shape of the container it's in.
So let's be a little bit careful with that. Adapts to container. So if I take, actually here, can I steal your drink?
$5.
What phase is in there? And I'm not, hopefully the people in the back can't see it. What phase is in there? Liquid. Okay, so let's ignore the solid for a moment. Liquid. So what I heard was that the liquid adapts to the container. Everybody see what that little blank space is up there? What's in that blank space? Not liquid. Isn't this the container? Does the liquid fully adapt to the container? If it fully adapted, what would be in that empty space? Liquid. So it's not fully adapting to the container. It's got a little bit of variability in its shape. So it'll change, but we want to be a little bit careful with the adapts to the container statement. So let's just call it variable. What's going to be its limitation on the shape it can take?
The amount there is.
The amount, or what we're referencing here, our volume. The volume for a liquid is fixed. It does not change, which means when I pour that liquid into the container, it will take the shape of the container up to the volume of the liquid, and then it can't occupy anymore. Right? It's what we've seen already. We're just trying to be careful with our terminology. So our adapts to the container is close, but it still doesn't quite cover that volume aspect. Right? If we switched all the way across to the gas, that was kind of a bad color right there. Let's go above. Gas. What's the shape? Okay. This one is highly variable. Okay. Whoops. Highly should have gone first, but I can get yelled at in my other class for that. Okay. Highly variable. What about the volume?
Variable again.
It's variable again because what is happening with our gas?
It's filling up to fire.
It will fill the container entirely. It adapts to the entire container. So when we're saying the shape back for our liquid, when we say adapts to the container, we have those kind of quotes in there, but that better fits under the gas system. Our gas will fill whatever container it's in. which means its shape is highly variable. It's dependent on the container. Okay? Our liquids have a limit, that being the amount of liquid there, the volume of that liquid. Kind of makes sense? Okay. Before we get into compressibility, let's jump back to our solid, because we didn't do the volume there. What's the volume for our solid? Also fixed. Let's try and come up with a picture that would detect or show these. So if I just had a particle, oops, didn't have as much space as I thought. If I have my particle here for my solid, my particle here for my liquid, and my particle here for a gas. That's the single smallest piece of it. Right? To be able to determine what phase there is, I need more of those particles. Right? So where would I draw those particles? If I have a highly variable shape for a gas and a highly variable volume, where's the next particle going to be? Spread out. Spread out. It's going to go seek out all those individual corners of our shape or of our container. So we end up seeing lots and lots of space in there. Okay. What happens with our liquid? They're going to be a lot closer to each other, okay, because they won't spread out to the entire space. Okay. They still move around a little bit, but they're a little bit closer. Okay. And that's supposed to be an irregular shape, but I didn't do a very good job there. What happens with our solid? There's really no space between. It's sanely organized, super tight, close to each other. Okay? So we can't see that shape easily change, or the volume change as well. When we look at our liquid, our shape can change because those molecules can slip by each other. Those balls can slip around and shift. In the case of the solid, they can't shift. Which takes us then to our last statement, compressibility. What do you guys think? What's the compressibility of the solid? Almost none. Why? What does compression mean? They compact. How do things compact?
They squeeze together.
They squeeze closer to each other, thereby getting rid of what? Empty space. How much empty space is in the solid?
Close to none.
There isn't any, which means how can I compress it? Okay, I can't. I'm just going to say not because I can't spell negligible. I've already learned that lesson multiple times. How about the liquid?
It's hard to compress.
Liquids in general are hard to compress. There is space in there, but the compressibility is still relatively small. The distance between those individual units is still really, really, really tiny. Okay? Which means we really don't see much. Okay? Very little compressibility within liquids. It's more than a solid, but not by much. What happens with a gas?
Oh yeah, you can compress that.
Tons of compressibility because of all of that empty space. What happens if I compress that gas down and keep compressing it and keep compressing it? We'll just call that huge compressibility. Eventually, what happens to that gas? It liquefies. I'm now getting those particles so condensed down that they can't move away from each other, and it transitions into the liquid. What happens if I keep compressing it? I can turn it all the way down to the solid. So we end up noticing with our phases that we can actually change phases a couple different ways. One, through this concept of compressibility. Okay, that's the harder one. What's the other one? Temperature. If I increase the temperature, what I end up doing is increasing the motion of those individual particles. Well, the more they move, the more they're going to space apart from each other, and the more likely I transition up, if you want to call it up our phase tree. Kind of makes sense? Okay. Because of the size of this class, we're going to add a little thing here. We're going to try, because it seemed to kind of work in a different class, the thumb rule. Okay, so I might ask for thumbs. Thumbs up means you agree with the statement I'm making. Thumbs down means that you disagree. Or let's just say randomly through it, you're like, this is boring. Okay. What I'm assuming by boring isn't just boring and I don't want to listen to you because you're monotonous, but boring, I already understand this. Does that make sense? So how are we doing with this? Is this good? Okay. Let's advance then. Matter. So we've got these individual phases that make up matter, but now what happens when I look at those different phases, can I further classify those down? And we end up with two different types of classifications, at least initially. Mixtures and pure substances. Right? A mixture really just means I have two substances or two pieces of matter near each other. Not bonded to each other, but near each other. A pure substance is chemically linked. It's bonded. Okay, well, this is the lowest level chemistry class you can get at the community college. Okay, so theoretically, you have not had any chemistry knowledge, which means your concept of the word chemical is limited at best. And yet, what are we, third or fourth slide, at the beginning of the semester, we bring up this concept of pure substances being different from mixtures because they are chemically linked. Well, what the hell does chemically mean? That's the point of this entire class. By the end of the class, you know what chemical means. Why are we addressing it now? Because that logical leap is something that we've just decided to kind of ignore and just move over. Okay? So let's work through a kind of example for those two that kind of works at a macro scale. If we look at all the people in this room, okay, are we chemically linked to each other or are we spatially linked? Spatially linked. You can get up and physically walk away. Okay? How about my index finger on my right hand? Okay? Is that chemically linked to me, or is that the mixture of the things that makes me me?
Chemically.
That is chemically linked. I can't just physically go, boop, there goes the finger, unless we had that weird magic trick with the thumbs that I don't know how to do. Right? No, it didn't work. Right? So chemically linked means it's physically attached or chemically attached, and that's not easy to separate away. Mixtures are spatially linked, so we can separate them by moving through physical changes. Well, at this stage, we really only know our physical changes because we've seen those before. That's our solids, liquids, and gases. If we can physically separate through those different phases, we're looking at a mixture, not a pure substance. Okay? So let's jump to the mixture. We have two different types of mixtures, heterogeneous and homogeneous. Okay? I added these extra words. Heterogeneous is a visible separation. Homogeneous is no visible separation. What do I mean? Can we come up with an example of one of each of those?
Alloys and solutions would be homogeneous.
Okay, just a sec. I heard oil and water. Then I heard alloys and solutions. Okay. Alloys, both those answers are correct. Okay. How many people have seen oil and water before? How many people are aware that they've seen alloys? Okay, that's where that one becomes dicey. Okay, it's not wrong, it's right. Okay, and then solutions. We've all seen solutions, but that one's a little bit vague. I want to pick up an example solution. Can you give me?
Alcohol is a solution.
So we're going to switch that a little bit, be a little bit less vague with that. Let's actually brand it out. Vodka is a solution. What is vodka a solution of?
Rotten potatoes.
The fermentation products of rotten tomatoes. Yes. Potatoes. Ethanol. And water. Okay. Versus oil and water. Okay, where have you seen oil and water?
Salad dressing.
Salad dressing. Good. We're keeping in kind of the food vein. It's a good vein. Salad dressing versus mixed drinks. Okay? We're looking at heterogeneous and homogeneous. What is that separation that we're referencing? What do you got?
Oil and water hang out on top of each other. They don't mix. However, vodka and for the water, those kind of things, they mix together and you no longer can see they're two separate things.
So if we just looked at those two solutions, we see a line separating them apart from each other. There's a clear delineation. It's not fully an empty space, at least as our visibility can see, but there's a very tiny empty space between those, much like between our individuals. When we move to the homogeneous system, we have no visible separation. Right? We can't see the different lines between them. Okay? What those separations are actually referring to, or the way I would like to think about it, is phases. Heterogeneous is two or more phases. And homogeneous is one phase. Okay? So we take a look at the oil and water example. Oil is what phase? Liquid. Water. Liquid, at least in this example. Okay, they're both liquids. How is that two or more phases? They're two different types of liquids. Okay, so we do have two distinct liquid phases. What happens when we move to vodka? Ethanol on its own is a liquid. Water on its own is a liquid. And yet when we mix them, what happens? We get a solution which is by definition one phase. Make sense? Can I make it more difficult? Or some other examples. Let's try other examples. Let's try... got space? Yeah.
What other kind of liquid can we add to oil and water to have another phase?
Methylene chloride might dissolve in oil. It's going to be different compounds. You're just going to you'd have to know how they're going to be different from each other, probably separating based off of density. Methylene chloride would probably work. We can talk about adding more liquids in there if you'd like later. Salt and water. What phase is salt?
Solid.
Solid. What phase is water?
Liquid.
Liquid. Isn't that two or more phases?
It depends on the amount of each.
If we add salt in relatively small amounts, what happens?
It dissolves.
It entirely dissolves. Do I see solid salt anymore? No. Which means I've gotten rid of the solid salt. It has somehow disappeared, which is really just dissolved into the water, and I now have one phase. Is that one phase water?
It's liquid.
It's liquid, yes. Is it water?
No.
No, it's now officially a solution of salt and water. Kind of, sort of? Let's get rid of the salt and let's make sand and water.
There you go. That's not.
That now doesn't mix, which then means I get a solid and a liquid. I have two phases. That makes sand and water heterogeneous. Okay, we ready for the last one that I think is probably the most difficult of them, which is probably up for debate in some circles. Making this one a little bit more difficult, jumping straight to an example and not giving you two different things. What is fog?
Isn't it water and gas?
With the free air temperature and the dew pointer within 2 degrees, you'll get fog.
Okay, so we can go back to the meteorologist definition, which is fine.
Condensing of the outside air into.
And we might need that definition because we do live in Arizona and we see fog so rarely, at least here. Okay? So fog, we see this kind of weird cloudiness in front of us, right? Everybody's roughly familiar with the concept of fog? Is that heterogeneous or homogeneous?
It's homogeneous.
Okay, why is it homogeneous?
Because it's the air, which is gas, and it's mixing with the water that's in the air from the clouds, and it's coming, and you can't see both. You can't see the water and the air separate. It comes together to make this gray mass.
Okay, so you're saying the air is a gas and the water is?
A liquid.
Can you repeat that? So the air is a gas and the water is?
Liquid.
Everybody hear that? Air is a gas and the water is a liquid.
Except the water wasn't. It was a gas like that.
If it's a gas, guess what happens? You get probably this room, right? When this room heats up and we all start sweating, okay? That's our gaseous or liquid water turning into a gas that's now filling this room. Have we seen fog in this room?
No.
No. Gaseous water looks the same as any other kind of gas. We don't see a gas. So if it was gaseous water and gaseous air, which of course it has to be, we wouldn't see anything, which would mean no visible separation. Do we see something with fog?
Yes.
Yes. What are we seeing with fog? And this is where it gets kind of
It's a
difficult.
transitional phase.
It's not even a transitional phase. We are seeing liquid water, but we're seeing it in insanely tiny particles. How do we know those particles are there?
Does it collect on your skin?
We could collect on the skin, true. But if I jump into the shower, that collects on my skin too, and that's definitely two phases. I have liquid water there.
Some kind of reflection.
It's a light reflection. Light passes through air. Why does light not pass through fog?
Because there's
It's
water.
too thick.
It's encountering another phase. That other phase causes the light to bounce, and what ends up happening? We now can't see through it. There's fog. Fog is actually two phases. Such tiny particle size that it looks homogeneous. It can't be homogeneous. It's heterogeneous. I think that one's kind of neat. Okay. How about the other branch? Pure substances, things that are chemically linked. My finger is chemically linked because we can't physically remove it. Okay. There's always exceptions, okay, to chemically linked. We can't remove it easily. Okay? Just like we can't remove hydrogen from water easily. Okay? So don't start talking about, well, I can cut it off. Okay? I don't want to cut it off. Okay? Chemically linked. We then look at our chemically linked into two categories. Okay? If they are chemically linked with at least two elements, then we have a compound. If it's only one element, then we have an element. Well, that's good. We used the definition to define our term. Okay. What are our elements?
Substances cannot be broken down by chemical
Okay.
reaction.
The substances that theoretically cannot be broken down by a chemical reaction. Okay. They're the smallest indivisible part, at least until we learned more. Okay. So our elements we've got summarized up on our periodic table. If we've got a substance that is a pure one of those all by itself, then we have what is defined as an element. If I take, say, oxygen and two hydrogens and I smash them together so that they are now chemically linked to each other, I now have water, which is a compound. Kind of, sort of. That whole right side branch is the semester we're talking about. Okay, so as we learn more about what a chemical bond is, we'll start to evaluate and understand what's happening within that. That was a bad transition on that because I meant to ask were there questions. No. So we want to further classify our elements. So we've got metals. We'll skip metalloids for the moment, and nonmetals. Okay. Metals tend to be solids. They're lustrous, meaning they're shiny. Okay. Malleable. You beat them and they deform. Okay. Conducts heat and electricity. So when I take a pot and I put it on the stove and I turn on the heat, what happens to that heat? Has anybody done that? You took a pot and you put it on the stove and you turned on the heat. What gets hot? Okay, the pot gets metal, which is taking us to the next statement. Why is the pot getting metal? Why is the pot getting hot? It is conducting heat through it. Okay? So that if we then touched it, that heat has passed through. We can then feel that heat. So we use metals as our pots. Okay? We could take, anybody bought those nice silicone gloves? Right? Do we make pots out of silicone gloves? Why not?
It melts.
They won't melt, actually. If they melt, that would really suck for your hand. Okay? They're terrible conductors of heat. Silicone happens to be made up of something that does not conduct heat well. Well, that happens to be a nonmetal. Okay? So when we're looking at our metals and nonmetals, we're trying to come up with the bulk classifications between them. Of all of those, we really only have the ability to look at the first two. Why can't we look at the others? And yes, my word choice there was very careful. Can you look at the heat passing through a metal? No. What would we have to do? Measure it. We'd have to invent a tool to measure most of those things. So in kind of an obnoxious question, if we took a look at the things shown at the top of this slide, would those be metals or nonmetals? Well, they're solids. Okay, so that fits our metal category. The right column was our nonmetals. Those are also mostly solids. Yeah, it becomes difficult. What do we have left? Luster. Luster is shininess. Dull is not shiny. Right? So the things that are shown in those pictures would be metals. Those happen to be random pictures of metals that I dug around with. How about these? Nonmetals. Okay, the nonmetals become a little bit more difficult to take pictures of. Some of them are solids, but a lot of them are gases. Okay? And if I took a picture of the air, you're probably thinking I'm taking a picture of the thing behind the air. Okay? Or I could just take a picture of empty white space and put that up there, and that's not very helpful either. Okay? So in most of those examples, what I'm trying to do is pick materials that we've changed and made visible in some form or another. What happens with these? We do have kind of a process of elimination game potentially running out of this. What do those look like? Metals. Why are you saying they look like metals? They're shiny. Okay, they're shiny and they're solids. Both characteristics that makes them apply to metals. What if I told you I went through and stuck heat to them and I don't feel any heat transition through the material?
Could possibly be non-metal.
That could be a nonmetal. I hit them with a hammer and they shatter.
Non-metal.
Nonmetal. Okay, but they're shiny.
Rocks.
They're a little bit of metal. They're a little bit of nonmetal. They're a mix of both, which happens to be the metalloid category. How would we be able to tell the metalloids by just looking at an image of them? We can't. We have to do some extra experimentation on it. Either through doing a direct measurement by measuring heat transfer or swinging a hammer at them. Okay, but even swinging the hammer at them could be dangerous because those compounds could potentially be malleable. That could be one of the characteristics they're pulling from the metals. Okay? And then they're pulling all the other characteristics of the nonmetals. Kind of makes sense? Okay. So, we've got a periodic table of elements. This periodic table should look very familiar after every single one of your exams because this is the periodic table on the exams. There will be a few extra notations on it. Okay? So, our categories. We have a couple ways that we can classify our elements. We talked about phases, solid, liquids, and gases. When we're talking about our elements in those phases, we're talking about our standard conditions. Okay? So if I wanted to look at liquid iron, that's not going to be a standard condition because I would not be able to exist at that condition. So think of it that way. Can I exist at that condition? That's the phase that I'm looking at. Okay? Whereas if I stood in liquid iron, that would not be a very good result for me. Okay? Because we'd have to get that pretty hot. Okay? So we've got solid, liquids, and gases. We have metals, nonmetals, and metalloids. Okay? It might be nice if we looked at our wonderful organization and say that is a solid, that is a liquid, that is a gas. When we look at the table on the periodic or the projector periodic table, do we see any delineations? No. Okay? Well, that's kind of unfortunate. That's one of the reasons why it was kind of designed, was for testing. Okay? What about the periodic table on the floor over here that will eventually make it to the wall? Do we see anything different about it in comparison to the one up there? And don't tell me it's smaller. Give me something else.
It's in numbered order.
Numbered order. Take a look at the ones up there. Are those in a numbered order?
I guess that's
Okay, so they are all organized based off a number. That number at the very top. 1, 2, 3, 4, all the way through, right? What's that? Okay. You're noticing that there's a color difference on the periodic table up here. Some of those letters are black, some of them are red. How'd you know the red ones were gases? They're different, but there's also blue ones and white ones. I'm going to pause that. 22, you said. I was like, 42, really? Titanium. Okay? So I heard someone say TI. How'd you know it was TI?
first two letters.
First two letters. Titanium is spelled T-I-T-A-N-I-U-M. Okay? Spelling without looking at it is difficult. Okay? First two letters were TI. That worked. And then I heard iron. 26. And iron is spelled F... No, it's not. I-R-O-N. And yet our symbol for iron is?
FE for ferrous.
Fe for ferrous, or ferric, or fair, coming from Latin for metal, I believe is its root. Okay. So the first two letters do not always correspond to the name. We have to be careful with that. Okay. The periodic table does not belong to the English language, it belongs to the world. So depending on who discovered what element, they got to rubber stamp their name on it. Some of them become kind of fun, like europium. What was europium? It was discovered in Europe. Wow, that was creative. Or americium. Or if we change the pronunciation a little bit, Americum. Discovered in Berkeley. Okay. Berkelium. Discovered in Berkeley. Californium. Also Berkeley. Okay. So some of the names have very current modern applications. Some of them have very distant applications. Okay. So we'll get into the names in just a second. Metals, we had titanium, we had iron. We've got those nicely boxed in, roughly on our... Let's just color it in. Give me a non-metal. What was that? Helium. He. Because helium starts with He, that worked. Another one. Oxygen. Begins with O. Anyone else want to guess one? Krypton. Nice safe bet. What are we noticing? How about metals? Give me another metal. Gold. Yeah, it's AU.
That's the one.
We notice anything? Metals are all in red. Where are our metals?
In the middle.
Guess what sodium is? That's a metal. So I disagree with your in the middle. I will also add aluminum, which happens to be shiny, lustrous, solid, conducts heat well, conducts electricity well-ish. Enough, I guess, if you're an electrician. So I disagree with your middle statement. Where are the metals? Where are the nonmetals? The nonmetals are all located on the right-hand side. What is wrong with my pen? On the right-hand side.
Hydrogen?
We also have this weird one, hydrogen, floating up there as a nonmetal. Hydrogen, depending on the periodic table, is sometimes shown on the left. It is sometimes also shown directly above fluorine. Why would we put it above fluorine?
So it's on the right number.
so it's a nonmetal, so it fits there. Hydrogen's a weird species because some of its properties act similarly to that first column, which are all metals, but its general overall properties match best with the nonmetals. Where's our line? Left side of the periodic table, the most left, the more metal. The most right, the least metal, or the most nonmetal. Where are we going to transition between our metals and our nonmetals? That was our metalloids, right? Which, oh, this one didn't have it either. That sucks. Because I don't have it exactly memorized, but I think I got it. Our metalloids follow a staircase step, I believe like that. There should be a nice darker line signifying the separation between our metals and our nonmetals. Almost anything on that staircase step happens to be a metalloid. It's transitioning between the two. Okay? Is it exactly true? Well, aluminum is what? It's on that line, and aluminum is most definitely a metal. Okay? So how do we know which ones are the metalloids? Memorization. How many of you think I've memorized it? I have no clue. Literally no clue. No, I just guessed. I think my guess is right. Paul.
All right.
Right? You've got you've got it out, right? Does it show the staircase?
No, it's this some cheap piece of crap. Got it from the bookstore over here. It doesn't even separate.
Oh, well, sorry. I thought you had the answer there. Oh, here we go. I think I nailed it, yeah. So everything touching the staircase except for aluminum is a metalloid. Okay? And again, I don't have it memorized. Okay? Which means, should you? No. Not a big enough deal to worry about. What should you worry about? The metals and the nonmetals. You need to be able to differentiate those. So pick the extreme of each of those sides, you're set. Okay? The next part. If we look at this one, we could kind of cheat with the symbols because the names were written on there. Okay? This is a little bit closer to what you get on the test. The one up here at the front. Anybody see the names written on there? No. That's because you're expected to know the names. Okay? Well, there's only 118 now? 18 that you would have to memorize the name of, right? That's not that bad. It could be worse. Okay? It will get worse. Memorizing 118 isn't worth it. Okay? So we want you to memorize roughly 40 to 50 of them. I think it's about half. Okay? Which of those should you memorize? 1, 2, 3, 4. The first 4 rows, you should know everything in those. Okay? This is always something I got confused with, and it seems to be consistent for most students. The row runs horizontal. Anything in those first 4 rows, you need to know the name of. Okay? And at this stage, name and symbol. Why not memorize the numbers?
Because it's in order.
15.994 jumping to 18.9984. I wouldn't call that necessarily in order. I give it to you. I give you the numbers. Don't memorize the numbers. Okay? Memorize the name and the symbol that corresponds to it. Those first 4 rows, absolutely. Okay? Will you find others? Yes. Okay, one was already suggested. Gold as AU. Why memorize gold?
Because we use gold all the time.
Okay? We see gold everywhere. It's a common element that you guys are used to seeing, so of course we make you memorize it. Silver. Okay, platinum. There's a bunch of other kind of sporadic elements that are important for students to have memorized. Okay? I don't know what they are specifically. That's why we have a file that lists them all, because I have most of them memorized. Okay? Elements for memory, open that. Anything that is bolded, absolutely you need to know. You'll notice there's a lot more things on there that aren't bolded. Guess what those ones are? The rest of the department decided you needed to know those. I disagree. So I highlighted the major ones in that file. Okay? You need to know those because those ones show up a lot. The rest of them show up very sporadically. Okay? Not worth the effort to memorize. Make sense? So we good? Thank you, sir. And myths. Unit 4. Okay, this is where I would argue it starts to get fun, but it does require a lot of memorization. Okay? So be aware of that going in. We'll see a lot of scientists pop up and concepts. Okay, I did see an email. You are responsible for memorizing the scientist and the concept that they helped found. Okay? There's 5 big ones. Okay? If you download the slides, it's, I think, at the very tail end of Chapter 4 and 5 PowerPoints, it actually lists the scientists. Okay? I've added that slide in right after the scientists. Well, here, we'll just skip real fast so you can see it. Whoop, too fast. There it is. Those 5 scientists you need to know about. Right? Dalton, Thomson, Millikan, Curie, and Rutherford. One might jump out, because you all read everything, right? Which of those names does not sound familiar? Curie, because Curie's not in your textbook. We'll talk about why. I wouldn't just talk about her because she died horribly. She did die pretty horribly, but radiation. So Dalton, we're talking early 1800s. Dalton's atomic theory. He listed 5 things. So he went through with all of the experiments that he'd ever done, made some observations, and then tested those observations, and he found these things to be roughly true. Okay? An element is composed of tiny, indivisible, indestructible particles that he called atoms. Whoops, sorry. All atoms of an element are identical and have the exact same properties. Atoms of different elements combine to form compounds. Compounds contain atoms in small whole number ratios, and atoms can combine in more than one ratio to form different compounds. What's shown on the right?
His illustration of the periodic table.
Those 5 points.
On the right-hand side, the little elements thing, that's his periodic table. Okay. See how we have letters and symbols? He used circles and stars and snowflakes. If you look down below the first 3 rows, we now start to see like a circle next with a dot next to a circle. Guess what he was trying to represent? A compound. Okay, what was he representing at the very bottom? More compounds. Because he had more atoms, what did he have to do? He started to add more pieces, more of these circles and stars and snowflakes in to create his compounds. Okay? If we think about humans being built of atoms, we're looking at lots and lots and lots of atoms. How many of you want to draw the compound? Yeah, it's going to suck pretty something awful. So what we've done is modified some of his rules into the periodic table. We'll talk about where the periodic table is coming from, but ultimately it took years or hundreds of years to build and try and decide how to decipher and put it together. Dalton was one of those first people, and he came up with those cool theories. Okay, so we're talking early 1800s. He's stamping, this is what things are existing. Okay, or what all matter is made of. As you've already read the material, you might be able to look through that list and be like, wrong. Yeah, he failed a lot. In fact, a significant portion of those are actually incorrect. So let's see how we did with the reading. An element is composed of tiny, indivisible, indestructible particles. Wrong. What part of that is wrong? Indestructible. Not true. All atoms of an element are identical and have the same properties. That one's wrong in kind of a weird system. It's wrong because of all. What do you mean all? It's going to come down to the concept of neutrons. Atoms of different elements combine to form compounds. I take hydrogen and I take oxygen and I put them together, and what do I have? Water. Guess what? 3 is true. 4, compounds contain atoms in small whole number ratios. I can take 4.38 hydrogen atoms and I can combine them with 1.62 oxygen atoms. No. Okay? They have to be whole number ratios. We can't have any fractions. So guess what? 4 is true. 5, atoms can combine in more than one ratio to form different compounds. True. There's a horrible joke about 2 guys walking into a bar. One guy orders H2O, the second guy orders H2O2.
Oh.
And he dies. Boo. Yes, we can combine differing amounts of our individual elements to get different compounds. If you don't understand that joke, I don't blame you. If you really want me to explain it, I'll talk to you after class. Thomson model of the atom. Okay, so late 1800s now, talking like 1890s. Okay, we discovered 2 subatomic particles. We got a negatively charged particle called an electron. Okay, and if Dalton's principles were correct, I don't have electrons. I now have something smaller than electrons, and that's what Thomson's coming up with. By corollary, if I have electrons, I also have protons. Okay, so I've got these positively charged particles. Okay? Why would I know that to be true? If I prove electrons, why do I also necessarily have to have protons? They have to equal out. Charged things are bad. This is why you don't stick your finger in the electrical outlet, because coming through the electrical outlet is a bunch of electrons. Okay? They're very high energy and they want to neutral out. So when you stick your finger in it, guess what happens? They run through your body and into the ground to neutral out. That's not a pleasant experience, so we don't do it, right? Okay? At least not more than once. Okay, so we know that if we have these negatively charged particles, there has to be something to balance it out, because there are species that exist that don't react. Okay? An electron has a relative charge of -1, and a proton has a relative charge of +1. These are relative. They're not exact. Okay? I just know they're opposites of each other. The thing that I find fascinating on this is what allowed this discovery to happen. A vacuum. Okay? Electrons are high energy particles. Okay? They impact things. They're trying to neutralize, which means we don't just have electrons chilling and be like, oh, there's an electron, cool, take a look at that. Okay? It doesn't happen. Okay? So that if I don't have a vacuum, there's tons of particles there. And what happens the instant I form that electron?
It goes away.
It reacts with one of those particles, and I no longer have the electron. I can't observe anything. So the only way we could observe those particles is making sure there's nothing there. That means a vacuum. Not a vacuum cleaner per se, but a vacuum. Okay? So prior to 1800, we didn't know what an electron was. Dalton's theories, that's why he said they were indestructible, because he couldn't see smaller than that, because he didn't have the proper equipment to be able to do it. Okay? How do we end up discovering it? Well, there's a couple big things that come out all roughly about the same time. Radiation is one, okay? And then the fluorescence within a vacuum. We take a look at a tube, we seal it up, we pull all the air out of it, and we said, just for giggles, let's put some electricity at either end of it. Right? And what they ended up noticing was the tube started glowing. Why would the tube glow? There's nothing in it. Okay? The only way there could be something happening is if there's electrons. We could further mess with this by putting in magnets on either end of it. Magnets have a charge associated with it, a positive and a negative. They could see the beam change directions, which meant that whatever was coming out from one end to the other existed, number one, and it had a charge associated with it. That tube was known as a cathode ray tube, okay? Or I believe they actually initially called it a cathode ray gun. It was later developed into the cathode ray tube, which became our massive honkin' TVs. Right? You've seen those? The big, giant, okay. They existed. Okay? Big boxes. Okay? So once he's had these charges, he then said, okay, the atom must be divisible down. So he came up with his own model, his own theory to explain what atoms were. That's where we had electrons and protons. Okay? He went through and said the electrons are plums. Okay? So a big, fat, chunky piece chilling in a sea of positive charge. So there's positive charge everywhere else. This became known as his pudding model. Okay? They're just floating around, and that's his deal. That's the model he puts forward. So he's famous for the discovery of the electron and the plum pudding model. The plum pudding model becomes a little bit less useful because it's wrong. Okay? But the existence of an electron is still held to Thomson. Okay. 1911, group by the name of Millikan and Fletcher, okay, determined the exact charge of an electron. Okay, I only put this one in here because I think it's pretty fascinating. Okay? So they took this little box, right, and like a perfume thing, right? You squeeze a little button and it sprays a fine mist of perfume on you, except they put oil inside it. And oil has an interesting property because it can build charge. Okay? So they sprayed that fine mist of oil into this box. Of course, oil goes everywhere. You get the droplets going everywhere. But at the bottom of it, they cut a very tiny hole, okay, just a pinhole. Just big enough that an oil drop could fall in it. Underneath that hole, they ran a bunch of electric plates. Okay? And what they could do is modulate the current of the electric plates. Okay? So if I've got an electron falling down, an electron with a negative charge falling down, what they could do is change the current on those plates to make that bottom more negative. What happens if it gets more negative? One of the interesting features that we find with our electrons and protons is like charges repel. So if that bottom becomes more negative, what happens to the electron above? It goes back the other direction. So they could sit there and modulate the current just enough until what happened? It just sits. So you made an oil drop not move. That's really special, guys. Okay? It is really special because they could do a couple things now. They know the current that they've put in. They can also see through a microscope the oil drop just sitting there. Because they can see it, they can measure the size of the oil drop. They can now compare the size of the oil drop to the charge they've put in, which then means they can then calculate the exact charge on an electron. Okay? You're modulating electric current, you're looking at a microscope, probably going to screw it up a couple times, right?
So they did it multiple times.
So you did it multiple times. They probably did it thousands of times. Average the results to get this result. Okay? I think that is fascinatingly cool and stupidly difficult. Okay? The extra part that I like to talk about on this is Millikan gets primary credit for this because Millikan was the primary investigator. Right? If we compared research to, say, this class, Millikan is me. But you're turning in, say, remember that assignment where you're turning in an essay, right at the end? You turn in a really good essay. I say, that's pretty cool. I'm going to publish that essay. Who gets credit for it? In science, I get credit for it. In this class, you would get credit for it. Millikan was just the guy at the end collecting everything and saying, this must be how it works. And this is mine now. Fletcher gets virtually no credit. Okay? Except some people happen to add his name in. That's what I end up doing. But Millikan's the primary name for this. So this is one of the downfalls in science. Okay? Particularly graduate work. In graduate work, someone tells you what to do, you do it. You can even come up with your own experiment. They still get credit for it. Which is why when you graduate and leave them, you then perpetuate the system by telling somebody else to do your work, and then you get credit for it. Okay? So kind of a neat process. What do I want you to get out of this? Millikan, charge. How many numbers did I list off in that sequence? None, because I don't want you to memorize the charge. It's only there just because it's a string of numbers that looks cool. Okay? So Millikan and charge. Thomson and electron. Rutherford. Turns out Rutherford was a friend of Thomson. Not only a friend, but he actually worked for him. He was his graduate student. But after Rutherford graduated, he went on to build his own lab. Neat guy. Rutherford told one of his students to fire alpha particles at thin pieces of gold foil. Okay, so one of the things that we discovered at this point was alpha particles. What are alpha particles? They're radiation. Okay? They're a positively charged radiation source. So what alpha particles do is they have this mass that is positive, and it can then be projected at something. Okay? So it's coming from nuclear radiation. Well, we can't just go into the store and buy alpha particles. Okay? Somebody has to purify a system to make those alpha particles. That person was
Rutherford.
Curie. Okay? Madame Curie, among her husband and a guy by the name of Becquerel, went through several processes of purifying radiation and studying it. That radiation source could then be embedded in a box of lead with a tiny little pinhole on it. Okay, why do we want the tiny little pinhole? So we can aim the alpha particles where we want them to go. Okay? That was Curie's discovery, is that source of radiation. Oh, that's not a big deal. Get rid of the purification of radium, which is what they ended up using here for our alpha particles. Rutherford's experiment doesn't work because he doesn't have alpha particles. Okay? What about just impure? Could it just be random crap radiation that we find everywhere? It's not reliable enough, number one, to generate enough alpha particles to see anything, but then also, the biggest issue with that is it's not predictable. If I can't predict what's happening with the radiation source, I can't draw conclusions about what that radiation source is doing further on down the line. Okay? So Curie's discovery is really, really, really important. Okay? Some extra things to add to this. So important, she won a Nobel Prize for it. Okay? Pretty neat. Also, we're talking 1900, 1910. When did women get the right to vote? Well, a little whiles after that. Okay. What was, I mean, you can even look at today. We look at women's role in society in 1900s. Pretty crap. Okay. Drastically improved. Okay. Still not necessarily where it needs to be, but pretty crap. She was able to get into the lab, purify radium, so that the rest of science could then progress forward from that. That's pretty impressive.
How did she do it?
Okay. How? One of the things that kind of, I think, floats under the current and doesn't get discussed as much is going to come from the men she worked with being like, you're smart, you do this. Okay? And giving her the access to that material. If she didn't have the access to the material, she can't do it. Okay? So her husband was instrumental in that, as well as her partners, Becquerel and a couple other guys as well. Okay, were instrumental in that research. The next part of it, what happens? I come up with an awesome cure to cancer. What's the first thing I'm going to do with that cure to cancer?
Publish it.
Monetize it. I'm going to put a patent on it, make everybody pay to use it so that I make millions. Guess what they did with the discovery for radium? No patent. Open access. Which then meant Rutherford's experiment was cheaper. Okay, why did they do that? Science has all sorts of different mechanisms that allow it to move forward. One of those is monetization. But one of the problems with monetization is it then makes it expensive, and the average person doesn't have access to that knowledge. Right? Curie, in and of herself, is special, but then the sheer ability of not going through and monetizing it and allowing the world access to that information is even more amazing and fascinating to me. Okay? Hugely kind of magnanimous. Okay? So that's kind of neat, in my opinion. Okay? We're going to add some extra things to it. Not only did she win 1 Nobel Prize, she won 2. 1 in chemistry and 1 in physics. How many other people have won 2 Nobel Prizes in science fields? None. None. Okay? Only one person has ever done that, and that was a woman that didn't have rights. I think that's kind of cool. Right? Another kind of random, just sort of juicy fact on this. She was based out of France. I think originally she was Polish, but she was based out of France. Every country has their own national society, okay, for sciences. France had one as well. Okay? This is someone that won 2 Nobel Prizes, leads to massive contributions to science, should be part of that national society, right? Denied. She wasn't allowed in because she was a woman. Right? So I like the story of Curie for a couple reasons. Okay? One, it's neat and amazing the contributions that she was able to make, but it's also something to say we need to expand our horizons. We can't just say only white men can do science, because it's a load of crap. It's not true at all. Everybody can do science, and we need to get everybody into it. But we also have to be honest with it and recognize there's lots of failure associated with it. The biggest failure for Curie? Death. And not just, oh, I died. She died because of the radiation she was working on. Right? That stuff does kill, and they would just walk around with it in shirt pockets. Be like, oh yeah, whatever, it's just alpha particles. It's not like it kills me. Oh wait, it does. Okay? Most people that were working with radiation at that time ended up dying for that safety reason. Okay? You want to add another little pseudo bit of information? You all watched that ACS safety video, right? How many have actually remembered anything in it? Yeah, that's kind of what I figured. Do you remember the part where they were talking about a pipette and they said, do not use your mouth to suck chemicals up into a pipette? Okay? How many thought that was incredibly stupid? And you're like, why are you even putting that in the video? Guess what that was roughly 50 years ago? Standard operating procedure. That's what you did. Okay? Chemists live on average 10 to 20 years less than the standard population because of stupid stuff like that. Okay? When those old stupid chemists start dying, that life expectancy will go back up because we now have safety rules. Okay? So science is a good field. It's fun. Just pay attention to the safety aspects. Okay? So back to Rutherford. Got the alpha particle, fired it at this thin bit of gold foil. Okay? If Thomson's model was correct, okay, said we had a sea of positive charge and then our electron sitting just chilling in the middle of it. If I fire this massive particle at it, what's going to happen to that particle? It's going to fly straight through. Okay? Because it's radiation, what I can do is put up a bit of tape that detects that radiation. Okay? And this is the part that I like to add to it. Come on. Okay, if we look at that projector, you can see the screen goes all the way around. But what if Rutherford had just done this? Just put the detector at the other end. He now confirms Thomson's model. Okay? So if he went into that experiment saying, Thomson's awesome, I worked for him, he's a great guy, let's prove his theory right. He just puts the little thing up. Hey, look at that. Thomson's model's right. We now have the model of an atom that is a plum pudding, okay, which would be a horrible travesty. Okay? Instead, what does he do? Puts it all the way around. Why? Okay. I used to like to say that he didn't like Thomson. That is entirely false. They were like best friends and communicated all the time. Right? Why would you put it all the way around?
Because you're good at science.
You're good at science. You want to limit all possible variables. You want to see exactly what's going to happen. Right? And it's a good thing he did, because what did he end up noticing? Every so often, you would see some particles hit in completely weird places. How do you get that particle to bounce backwards? Okay. It had to hit something. And it had to hit something that was massive enough to cause that massive alpha particle to bounce, and positive enough to cause it to repel the opposite direction. What does this experiment prove? Plum pudding is wrong, and we have a nucleus. We know that nucleus to be supermassive and positively charged. Right? So Rutherford's model says we have protons in a nucleus. Right? That's pretty huge as far as our discovery goes. The electrons are then the sea around the nucleus. Right? Get an idea of size. If an atom, 10 to the minus 8 centimeters, the nucleus is 10 to the minus 13. 8 versus 13, right? That's only 4 years. That's not a big deal. Okay? But that power of 10 becomes very difficult for us to process. So let's scale it. If the atom is the size of the superdome, that's pretty big. The nucleus would be a marble sitting in the middle of it. That's a little bit larger than 4 years. Okay? So when we're looking at atoms, that nucleus is incredibly tiny. We're effectively looking at a point charge of putting all of those protons in one single space.
Did they use other types of oil other than gold?
I think they could theoretically, but one of the issues is making sure it's thin enough that you can see through it. Anybody have a problem with putting all the protons in one location? Like charges repel. If I put all my positive charges in the exact same space, what happens? They are flying away from each other. In the case of hydrogen, that's not a big deal, because hydrogen has one proton. But what happens when I move up to helium? It has 2 protons. And as soon as I try and put them in the same space, they fly away. Okay, so Rutherford's not a dumb guy, looks at it and says, well, that means something else has to be there. What something else has to be there? Stop being scientific.
Unknown charge.
An equal and opposite charge.
That means you put electrons in the nucleus. It's easier than that. You guys are being way too sciencey. Maybe I should have you stop reading the book. No, don't do that. Keep reading. A glue. I need a glue to hold the protons there. Okay? The more protons I put in, what do I have to do? More glue. Okay? What is that glue? That's our neutron. Okay? Rutherford postulates a neutron. Okay? That's one of his conclusions from his experiment. Okay? And that's because our like charges repel. Neutrons weren't discovered until, I think it's James Chadwick found out later. Don't worry about James Chadwick. I feel kind of like a jerk for saying that, but he discovered a neutron and proved it existed. Okay, so he backs up Rutherford's model. So at the end of all of this, what we end up with is a summary of our subatomic particles. Notice it's in a big red box. Why? It's important. You need to know all of that information. Okay? Probably don't need to know how to spell electron. You can probably just get it right. E. Why do we symbolize it as E? Because we're lazy, we don't want to write it out. So we just write it as the first letter. Okay? What's in the upper right-hand corner? The charge. We're saying the charge on that particle is negatively charged. There's our relative charge. Notice it says relative. This is not the absolute charge. Remember, the absolute charge was 1.953 times 10 to the minus 16 coulombs or whatever it was on those previous slides. I don't care about that number. I want to know relative charge. So the electron is charged negative relative to a proton, which is charged positive. The neutron, our glue, has no charge. So sometimes we'll see in the upper right-hand corner a 0 because 0 means nothing. Right-hand corner means charge. 0 charge. The next part is mass. Okay, it turns out electrons don't have a significant mass. Okay, and protons do. Now the question comes down to our neutrons. If we looked at hydrogen, it had 1 proton. What's the mass of hydrogen? 1. What are we summing? The number of protons. What happens when we move to helium? It has 2 protons. What's its mass? Not 2. What's that other mass? That's my glue. The glue carries a mass. That's the neutron. So our neutron is there and has mass, but it does not have charge. It's what helps hold those protons in there. Kind of make sense? So there's our cool for scientists. We'll move into atomic notation on Wednesday. And hopefully I'll try and pick up the pace a little more. How is the pace? You can continue to pack up. How is the pace? Slow?